We now introduce notation that will allow us to describe the behavior of functions. Let's start with x values. Given a number a, the phrase x approaches a from the right is denoted as follows. And this means we take x values larger than a itself and continually take these x values to be closer and closer to a, but never equal to a. In the very same manner, we can define the phrase x approaches a from the left. In the very same manner, we denote x approaches a from the left as follows. And this phrase means we take x values that are smaller than a and allow these x values to get extremely close to a, but never equal to a. There's two more ways we'll discuss how x values behave. The first is as x approaches infinity and is denoted as follows. And this translates to mean we want to have all our x values grow unconditionally so that our x increases without any kind of bound. And this can be seen on the graph down below. And the other case again is as x approaches negative infinity. And what this means is we want our x values to grow unbounded again in the negative direction. Or we want our x to decrease without any bound at all. This is denoted as the following. And an example of this phenomenon is shown on the graph in green. Now that we can describe the behavior of x values, we turn our attention to y values. Suppose we want to study the y values of our graph as our x values approach 0 from the right-hand side. Then we're looking at x values that are larger than 0, but are getting closer and closer to 0. These x values are mapped to points on our graph, which are getting higher and higher as our x values are getting closer to 0. In other words, our output is approaching infinity, which means our y values are increasing without bound, and this is denoted as follows. On the other hand, suppose we're looking at x values approaching 0 from the left-hand side, then our x values are smaller than 0, but they're getting closer and closer to 0. These x values correspond to points on our graph, and the y values of these points are growing larger in the negative direction. In other words, they're decreasing without any bound at all. We call this behavior y is approaching negative infinity, or f of x is approaching negative infinity. In this final case, let's see what's happening as our x values are approaching infinity. Then our x values are growing larger and larger over time without any bound. And again, this corresponds to points on a graph. And these points appear to be flattening out. We call this behavior f of x is approaching some number a, and in this case it appears that our f of x value is approaching 0. In this problem, we want to find the end behavior and local behavior of the following graph. First, let's go ahead and look at the end behavior. We want to see what happens as x approaches infinity, where are our y values going. So first, as x approaches infinity, we're looking at this set on our graph here. So here's our x values. Then we're looking at this portion of our graph, and it appears that our y values on our graph are approaching the line, the blue line here, which is given by 3. And now if we look at our x values as we're approaching negative infinity, then this is going to correspond to these x values here. And this is the following portion on the graph. Again, it looks like our y values are approaching the blue line, which is y is equal to 3. And this is telling us about the end behavior. So now that we've completed our study of the end behavior, let's go ahead and look at the local behavior. The local behavior is going to be everything but the end behavior. So let's go ahead and see what we have left. We have all the x values that are approaching -1 from the left-hand side, and all the x values approaching -1 from the right-hand side. We'll look at the left-hand side first. Now, as x approaches -1 from the left-hand side, we're looking at all these values over here. And this means that our y values correspond to these points on our graph, and it seems that our y values are approaching negative infinity. Now we'll go ahead and look at our x values approaching -1 from the right-hand side. This corresponds to the following points on our graph, and the y values of these points are also approaching -infinity. And so we're done looking at the local behavior. In this problem, we encountered two different lines. The first one was a horizontal line, which was blue, and a vertical line, which is green. Both of these lines are known as asymptotes, and we can rephrase the definition of an asymptote in terms of our arrow notation. If we have that f of x is approaching positive infinity or negative infinity as our x values approach a point A, then we say our graph has a vertical asymptote at x is equal to A. In the picture on the left-hand side, we would have a vertical asymptote here. Now, if our x values are approaching positive or negative infinity, and we have that our y values are approaching some constant b, then we say we have a horizontal asymptote at the line y is equal to b. The graph on the left-hand side would have a horizontal asymptote at the following green line. Let's sketch y is equal to 1 divided by x squared after shifting it right 3 units and down 4 units, and see what happens to our horizontal and vertical asymptotes. The graph y is equal to 1 divided by x is given by the following. We can see that we have a vertical asymptote at x is equal to 0, and we also have a horizontal asymptote at y is equal to 0. Then, if we're shifting the graph right 3 units and down 4 units, we'll also be shifting our horizontal and vertical asymptotes by the same amount. That means we'll have a vertical asymptote at x is equal to 3, and we'll have a horizontal asymptote at y is equal to -4. Then the shape of our graph is going to look exactly the same, which means our graph will look something like this. And we're done.